Hello everyone, this is Professor T Square. This is a video series on OPAMP. The series will consist of 3 videos. In the first video, we'll be discussing about the basics of OPAMP, non-inverting and inverting terminal and open loop OPAMP. In the second video, we'll be discussing about closed loop OPAMP, summing amplifier, OPAMP circuits with resistors and capacitors. In the third video, we'll be discussing about circuits with multiple OPAMPs, spatial OPAMP circuits, and positive feedback OPAMP. This is the first video of the series, and I recommend you to watch the video in order so that you can have a better understanding. Okay, now let's start. OPAMP. OPAMP stands for operational amplifier. This is the circuit symbol. It consists of 2 inputs. The one with the negative sign, this is known as the inverting, and the one with the positive sign, this is known as the non-inverting. It has 2 power supplies, terminal, plus VCC and minus VCC, and we have an output terminal. Now, OPAMP can be connected in 2 configurations. One is known as a closed loop. The other one is known as the open loop. So, in the closed loop, the output will be connected to the input, and in the open loop the output will not be connected to the input. First we'll discuss about open loop, and later on we'll discuss about closed loop. Now, to understand what is the inverting terminal and non-inverting terminal, let us consider a circuit here. Let us ground the non-inverting terminal and let us supply a signal at the inverting terminal. Suppose this is the signal. Then at the output, we will get an amplified inverted signal. Similarly, if I take another circuit, and let's say this time we will ground the inverting terminal, and we will supply a signal here at the non-inverting terminal, then at the output, we will get an amplified signal, but it will be of the same phase. What suppose if we give input to both the terminals? Say here in this case, I am not grounding any one of them, and we are supplying one signal here, another signal here. So in this case, the output will be given by the gain into the difference between the 2 input. Now, generally, the gain here, AV, this is the open loop gain. This is the open loop gain. Now, this gain, AV, is generally of the order of 10 to the power 5. So, the gain is very high. So, let us take a simple example. Let's say the V input is 10 to the power minus 3 volt, that is 1 millivolt. And let's say the power supply is plus minus 15 volt. Now, if I express the gain in terms of the output and input, then it will be V naught by V in. Here V in is the difference, this term. This term I am denoting it by V input. Then V output will be given by AV into V input. So if I do the calculation here, it will be 10 to the power 5 into 10 to the minus 3. So V naught will be equal to 100 volt. Now, if you see carefully, this V naught and the power supply voltage. Now remember this, the output cannot exceed the supply voltage. So what will happen is, the output will be driven to saturation. And this saturation voltage, we denote it by V saturation like this. And this V saturation it is generally 1 volt to 2 volt lesser than V supply. Now, let us consider this circuit. Here, input is given to both the terminals. So, the net input will be V1 minus V2. And since this is an open loop, because the output is not connected to the input, the gain will be of the order of 10 to the power 5. Now, if the input is of the order of 1 millivolt, or say it is of the order of 1 volt or higher, then the output will be driven to saturation. Now, the next question is, which saturation it will be driven to, whether it is plus V saturation or minus V saturation. Now, this will depend on which voltage is higher. Suppose if V1 is greater than V2, then in this case it will be driven to plus V saturation, and if V1 is less than V2, then it will be driven to minus V saturation. Now, suppose let us take one example. Let's say here the input is plus 2 volt and here it is 1 volt, plus 1 volt. So in this case, the input at the inverting terminal is greater compared to the input at the non-inverting terminal. So the output will be driven to minus saturation. Now suppose in the question, if the saturation voltage is not given, then you can approximate V naught, that is output, equal to minus VCC. Now sometimes they give a circuit like this. Suppose this is V input, then this is connected to a network of resistors. Let's say this is R1 and this is R2, and this is fed to the OPAMP. In such type of situation, you should note that even though V in is the input voltage, the net voltage which is supplied to the OPAMP is the voltage at this terminal, let's say Vx. So what you have to do is, you have to calculate this Vx, that is the voltage drop across R2. So in such type of situation, what you have to do is, you have to use the voltage division rule. So voltage division rule, Vx is equal to R2 divided by R1 plus R2 into V input. This, you have to use this. Now, sometimes in the place of a resistor, sometimes they might use a capacitor. So in that case, let's say I will just draw an example here. One resistor here and one capacitor here. And let's say this is grounded, and let's say this is R and this is C. This is the input, but this is fed to OPAMP. In such type of situation, you use the impedance of a capacitor in the place of R. So in this case, let's say this is the Vx, then Vx will be equal to Xc divided by Xc plus R into V in. Now, using the concepts which we have learned till now, let us try to solve a numerical here. This was asked in GATE 2012. So the question says that an OPAMP circuit is given and you are supposed to find the output voltage, and the input voltage is given here, V in. This is a linear voltage. Now if you see this circuit, this is an open loop circuit because the output is not connected to the input. At the same time, this V in is directly fed to the non-inverting terminal, but this plus 5 volt, it is fed to the inverting terminal through a network of resistors. Now, the first thing which we have to do here is, even though 5 volt is supplied here, the net voltage which is going inside the op-amp is this particular Vx. I'll just denote it by Vx. So Vx is 1 kilo ohm divided by 1 kilo ohm plus 4 kilo ohm into 5 volt. So if we do this calculation, we will get 1 volt. So now we have got Vx. After getting this Vx, now two cases can arise here. So one, I'll call it A. So if the input is greater than 1 volt, that is, the voltage at the non-inverting terminal is greater than the voltage at the inverting terminal. So in this case, the output will be driven to plus V saturation, and since the V saturation value is not given, so we can approximate by 10 volt. Second case is the V input is less than 1 volt. That is, the voltage at the non-inverting is lesser than the voltage at the inverting input. So in this case, V naught will be driven to minus V saturation, which is approximately equal to minus 10 volt. Now let us come back to this graph here. So if we can see this point, so in this region, the input is lesser than 1 volt. That is the case B. And after this, it's case A. That is, the input is greater than 1 volt. So if I draw a line here, so for case B, the output will be driven to minus 10, and for case A, the output will be driven to plus 10. So I can just indicate one marker here, 10 volt, and one here, let's say minus 10 volt. So in case B, it will be minus 10, so the graph will be here, and after this point, the graph will be here. So this is the answer. Now, compared to the previous circuit, this circuit is different because V2 is fed through the resistor R1. In such type of situation, we can use a golden rule, and the golden rule is, for an ideal op-amp, the gain tends to infinite, and also the input impedance also tends to infinite. Because of this, the input currents will tend to 0. So the current at the inverting will be equal to the current at the non-inverting, which is equal to 0. Now this leads to a condition, that is, V at the inverting will be equal to voltage at the non-inverting terms. Now if we come back to this circuit, I'll denote this as Vx. So Vx is the voltage and inverting, and this one I'll call as Vy. So Vy is the voltage at the non-inverting terminal. Now using this concept, we can directly write Vx is equal to Vy. Now Vy we can calculate easily by using the voltage division rule. So it will be equal to R3 divided by R2 plus R3 into V of 1, and this will be equal to Vx. So now using this concept, let us try to solve a numerical. This question was asked in CSIR-UGC NET exam 2012. So you are given a circuit and you are told to find the voltage at A. Now using the previous concept, the voltage at A, I'll just denote it VA here. This voltage should be equal to the voltage at this point. I'll call it VY. So VA is equal to V of Y. Now V of Y we can calculate by using the voltage division rule. So 1 kilo ohm plus 1K plus 1K into 1 volt. This gives 0.5 volt. So VA is 0.5 volt. So option B is the correct answer.